You guys are going to learn the general multiplication rule and tree diagrams today. This first equation that's up here is a review. Okay, we did this already. Suppose that A and B are two events resulting from the same chance process. We can find the probability of A or B with the general addition rule. So you guys, whenever you see or, that means we are adding, okay? So that's just the review for the general addition rule. If there's or, we add probabilities, and again, you're subtracting the double count, which is the and part. Okay, this is one you already know. Some of you want to write it down anyways, which is fine, but if you are. Okay, how do we find the probability that both events happen, meaning the probability of A and B, if it's not given to us, okay? We're going to start with the conditional probability formula. So this conditional probability formula, you guys, is on the exam. It's given to you, okay? And this is one that you should memorize and love and learn, and we just did it last Friday. Okay? How do we read this piece right here? Raise your hand if you remember how to read this. Maddie. Already happened, right? What's the probability that A happens given that B already happened? So now we actually want to find an equation for probability of A and B occurring. Well, the probability of A and B occurring is this piece right here. Okay? So we can manipulate this formula to find this by multiplying both sides by the probability of B happening. So this formula is not given to you, but this one is. So all you have to do is multiply by this probability, and we get the probability of B times the probability of A given B is equal to the probability of A and B happening at the same time. So again, and from our old school days, and means multiply. Did you guys ever learn that? Or means add in math, and means multiply. Okay. This is called the general multiplication rule. Okay? So the probability of A and B looks like this. This symbol, by the way, means intersect. And again, this is like when you have those Venn diagrams, it's the overlap in the middle. So we multiply the probability of A times the probability of B given that A happens. In other words, this rule says that for both of two events to occur, the first one must occur, and then given that the first event has occurred, the second must also occur. Okay? So the first one has to occur, and then given that that occurs, what's the probability that the other one occurs? Okay? So there is some conditional probability inside of this formula. All right, so let's try an example. Yeah, you want me to go back? Okay. The Pew Internet and American Life Project find that 93% of teenagers ages 12 to 17 use the internet, and 55% of online teenagers have posted a profile on a social networking site. I bet that's higher than 55, but I don't know. Find the probability that a randomly selected teen uses the internet and has posted a profile. So two things happening. So let's write this out with our probability, how it would look. So we would do the probability that the teen is online. And, so that's this symbol, uses the internet and has set up a profile. So we'll put has a profile. Okay, so probably they're online and they have a profile. So the formula is, well, first we have to say the probability that they're online, and we're going to multiply that times the probability that they've got a profile given that they're online. Okay, so the probability that they're online times the probability they have a profile given that they're online. This one's super easy because they give us those probabilities. We don't have to do anything to find them, right? So what's the probability that a random teenager is online? Okay, it's 93%, so 0.93. And then it gives us the next one too. Given that they're online, what's the probability that they have a profile on social media? 0.55. Okay, so it's just the general multiplication rule, right? We want this and this to happen. We multiply them together, and we get 0.5115, which means we do need to answer the question in a sentence. There is about 51% chance that a randomly selected teen uses the internet and has posted a profile on a social networking site, okay? The hardest part is probably setting up the formula. Okay, but multiplication hopefully is a little bit intuitive to you guys with and. Let's try another one. The general multiplication rule is especially useful when a chance process involves a sequence of outcomes. In such cases, we can use a tree diagram. All right, we're going to use tree diagrams. Get excited. Tennis great Roger Federer made 63% of his first serves in the 2011 season. When he made his first serve, he won 78% of the points. When Federer missed his first serve and had to serve again, he won only 57% of the points. Suppose we randomly choose a point on which Federer served. So we're going to make a tree diagram based on this, and then we'll answer questions. You guys can write down this tree diagram with me. Okay. So first serve, we've got a couple things. Draw a little arrow for our tree diagram. Okay, so he's either going to make or miss his first serve, right? So there's a 63% chance that he's going to make the first serve. So I'm going to put a 0.63 here, and what that means is that he makes his first serve. Okay, they didn't give us the other probability, but we can find it pretty easily. If he doesn't make his first serve, what's that probability? So if there's a 63% chance he makes it, there's a 0.37 chance that he doesn't make it. Okay. Now that's going to branch out, right? So now we have another thing that can happen here. So this tells us, so he makes the first serve. When he makes the first serve, he wins 78% of the points. So if he makes it, that's over here, he wins 78% of the points. So wins the point. Okay, so also when he makes the first serve, what's the chance of losing it? They don't give it to you, but we subtract from 1, right? So if there's a 78% chance he wins the point, there's a 22% chance, lose point. Okay? My boxes are not very good. All right, and then when he doesn't make the serve, so they give us that probability as well. So come back up here, and it says when Federer misses his first serve and had to serve again, he only won 57% of the points. So we put a 0.57 here. He still can win, right? Wins point 57% of the time if he misses that first serve, which means he's going to lose the point the rest of the time. So 43%. Okay? Everybody good with that? So that's how you make a tree diagram. Now we got to answer our question. So let's see. Is there a set of branches? We already did that. Blah, blah, blah. All right. When Federer is serving, what's the probability that he wins the point? Okay, just the probability that he wins the point. Well, there's two ways we can go about finding this. He wins the point here when he makes the first serve, and he also wins the point here even when he doesn't make the first serve. So we have two probabilities we are going to add up because they're mutually exclusive, we are using the general addition rule after we use our multiplication rule. So the first one, we want the probability that he makes the first serve and, so our symbol looks like this, wins the point. Okay? And there's a second way we can get the probability of winning, right? The probability that he misses the first serve and still wins the point. So those are our two probabilities. Again, we can multiply them together. So we multiply our probability of, I'm going to put M for, I'll just put makes first serve times the probability that he makes the first serve given he wins. Sorry, running out of room. So this is just that formula. So the probability that he makes the first serve, so we look back at our tree diagram, and this is much easier without thinking of the formulas, but you do need to think of the formulas to make sure you know what you're doing. My mouse is not liking up. Hold on. Hold on. And we're back, maybe. Okay. There we go. All right. So what's the first probability for making the first serve? It'd be 0.63. And what's the probability we win the point? 0.78. Both of those have to happen. So we're going to multiply 0.63 right here times 0.78. Okay? Multiply those together, you get 0.4914. Oh dear. My mouse is freaking out. All right, and for the other one, similar, right? We want to multiply the probability that he misses times the probability that he misses given that he wins the point, right? So what's the probability of missing but still winning? That's this track here. We can multiply these together. So the probability doesn't make serve times the probability of winning, so 0.37 times 0.57. That's our other way to win the point, is 0.2109. Okay. Now we just add those together. So multiply down the tree, okay? And now I want to know what's his probability of winning. Well, there was two ways. He can make the serve and win the point, or he can lose the serve and win the point. So we're going to add those together. This plus this. I really wish I could see my mouse. And that's 0.7023. So you would write a sentence, Federer wins about 70% of the points when he is serving, right? This is only when he's serving as opposed to when the other guy's serving. That's pretty good. Pretty good. All right. Suppose you were watching a recording of one of Federer's matches from 2011, and he's serving in the current game. You get distracted before seeing his first serve, but you look up in time to see Federer win the point. How likely is it that he missed his first serve? So this is a conditional probability. So we want, what's the probability that he missed, right? What's the probability he missed, given that he still wins the point? Okay, conditional probability formula. Who remembers this formula? We just wrote it down in our notes. Hopefully you guys have it right. Ginger? Yep. All right. So the probability of missing and winning. So what's the probability of missing and winning? We actually just found that. So he misses the point and he wins. Which probability was that where we found that? Donovan? Right here, okay? We just found that. Misses first serve and still wins point. So that's 0.2109. That goes in the top, 0.2109. Divided by the probability of winning. Well, we just found that too. The probability of just winning, whether he hits the first serve or not, is 0.7023. All right, so our conditional probability, so chances are, what do we get on that? About 30%, 0.3003. So you would write a sentence, there's a 30% chance that he missed the first serve. All right, little YouTube example. I think I'm gonna, let me think here, if I want to do this one or not. I thought this one was more interesting. Let's do this one. I feel like 2 would be a lot for you guys. We'll see if we can do this. All right. Many women choose to have annual mammograms to screen for breast cancer after age 40. A mammogram isn't foul-proof. Sometimes the test suggests that a woman has breast cancer when she really doesn't. That's called a false positive. Other times the test says that a woman doesn't have breast cancer when she actually does. So that's called a false negative. All right. Suppose that we know the following information about breast cancer and mammograms. 1% of women age 40 or over in this region have breast cancer. For women who have breast cancer, the probability of a negative mammogram is 0.03%. And for women who don't have breast cancer, the probability of a positive mammogram is 0.06%. Okay, so the test can mess up. And we want to know if we randomly select some woman over age 40 who did actually test positive for breast cancer, what's the probability that she actually has breast cancer? Okay, so let's make a tree diagram. So we're going to start with this right here. 1% of women in this region have breast cancer. Okay, so we're going to make our tree diagram. So 1% is 0.01. Okay. And that means that 99% don't. All right, then it says, for women who have breast cancer, so you actually have it, the probability of a negative mammogram, that would be bad, right, so they don't detect it, is 0.03. So from the ones who actually have breast cancer, we've got 0.97 who are going to test positive, and 0.03 who are going to test negative. So test positive, as they should. This group should test positive, right? And down here, this group tests negative, which is not good. Okay, and on the other side, we have people who don't have breast cancer, and the probability of testing positive is 0.06. That's a little scary, right? So 0.06 of those people who don't actually have it test positive anyways. Which means the remaining, so 94%, test negative. Okay, so what's the probability that they tested positive, but they actually don't have it, okay? Let's see if we can figure that out. Or actually, what does it say? Probability that they have breast cancer and they tested positive. All right, so the probability that they have breast cancer, given they had a positive test. So if we write this out using our formula, this is our conditional probability. Probability of having breast cancer and a positive mammogram divided by a positive probability of a positive mammogram. Okay, so the top part, the probability of B having breast cancer and testing positive. How do I find that probability, just the numerator? Anyone tell me how we find just this? Probability of B and P. just have to multiply two things together. Anyone know what those two things are? Ginger?
The probability of C given D times the probability of C.
Okay, which is what? So the probability of this one, multiplying by the probability of this one given this one. So we're just multiplying these two together. Okay? Probability that you have breast cancer and you tested positive means we multiply 0.01 times 0.97. Okay. Divided by the probability of testing positive. There are two ways to test positive, and we have to add them together. Anybody know what I would put in the denominator? Similar to what we did in the Federer example, where we added them at the end, right? There were two ways of winning, and then we added them to get the total. So this is the same thing. So to test positive, we have this way here, 0.01 times 0.97. Or there can be this way here. You can not have breast cancer and still test positive. So we add 0.99, I'm sorry, I ran out of room, 0.99 times 0.06. Okay, so multiply that plus multiplying that. Those are our two ways to test positive. So in the numerator, there is a 0.0097 chance of having breast cancer and testing positive. In the denominator, there is a 0.0691 chance of just testing positive. Okay? If we divide those probabilities, it is 0.14. What does this actually mean? This means, given that you randomly select a woman that has tested positive, there is only actually a 14% chance that she has it. So that's kind of good, right? Interesting? No? You guys need another example of this? You guys were a little quiet. I don't know. It was nervous that maybe you need another example. All right, well, you guys can do this one with me then. This is the last one. A computer company makes desktop and laptop computers at factories in 3 states, California, Texas, and New York. The California factory produces 40% of the company's computers. The Texas factory makes 25% of the company's computers, and the remaining 35% are manufactured in New York. Of the computers made in California, 75% are laptops. Of those made in Texas and New York, 70 and 50% are laptops, respectively. All computers are first shipped to a distribution center in Missouri before being sent out. Suppose we select a computer at random from the distribution center. So you guys construct a tree diagram. All right. Delaney, what's one way that you can be a laptop? You're going to do what? Yep. Yep. Good. So one way is you are in California, and then given that you're in California, it's a 75% chance. So we multiply those together. Okay? And another way is this times this. 0.25 times 0.70. And another way is this. 0.35 times 0.50. Okay? Those are this probability given this. This probability given that this happened. All right? And then we add them all up to get the total probability of it being a laptop. So you get 0.65. Make sense? So multiply down your tree diagram and then add them all up. So no special formula on that one, really, even though we were using the formula technically. It's much easier to just look at the tree diagram, probably. No, unless you are not given a tree diagram, and then you would. Okay? Given that a laptop is selected, what's the probability it was made in California? So you guys, this is conditional probability that we learned Friday. Given that a laptop laptop is selected, what's the probability it was made in California? You want to start with, all right, we're looking for the probability it was made in California given that it is a laptop. Use your formula for this. And then some of the probabilities you found in A will help you with, or in number 2 will help you with this one. All right, so our formula is, it's probability of California and laptop. So probability of California and laptop, you guys, is, we already found part of it, right? California times laptop. What decimal did you guys get when you multiplied those together? Okay, 0.3 divided by our answer to the last question here. What's the probability of laptop? We just did that one in the last one, so it's 0.65. So divide those and you get 0.462. All right, good job if you got that. So 46% chance that given a laptop is selected, that it was made in California.